people!
Hello, yearbook people.
Oh, they're so excited. First period this morning. Okay, I about started, and then a couple of them, Amelia and Phoebe, kind of reminded me, like, hey, aren't you supposed to be recording this? Yep, sorry. Okay, so we're starting with multiplication. Multiplying probabilities. What was I going to write down? Oh, more than one thing. You are multiplying when you have a compound event, which means more than one thing. Like you are drawing two cards. Draw two cards. Or roll 3 dice. It doesn't have to be 2 always. It can be just anything more than 1. Roll 3 dice. Or spin a spinner and then roll it, and then flip a coin. How about that? So it doesn't have to be 2 of the same thing or 3 of the same thing. I could spin a spinner on one side and roll a die or flip a coin on the other side. So just 2 things that are happening, and we want to know the chances of both of those occurring at the same time, all right? So I'll zoom out here just a second. Okay? All right, so we have what's called independent events and dependent events. So when I'm selecting a card, here's my big fat deck of cards, and I'm going to have India and Colton over here. They're going to select a card, okay? So we'll let Colton go first, since he's like the only, well, 2 boys in here. Okay, so he picked a card, and he can show us his card. It's the 5 of clubs. Is that a club? Yeah. 5 of clubs, okay? Now, he's going to put that card back in there, and his chances of choosing the 5 of clubs, or any 5 in general, I guess, is 4 out of 52, right? Or the 5 of clubs is 1 out of 52. There's only 1 out of 52, right? That is a 5 of clubs. Now, India is going to draw now, and he put his card back in. So how many cards is she drawing from?
52.
Still 52, right? And India drew the... Draw again. She drew like the weird cards that come with me. King of Hearts. That's a good card. King of Hearts. Okay, so now India could have very well drawn the same card as Colton because he put it back, right? So those 2 things were independent of each other. It did not matter because India had equal chance of drawing the same card as what Colton did. She had all of the cards to choose from. Versus Colton choosing a card, and it is the 9 of clubs. Club? Yeah, 9 of clubs. He likes the clubs. And now India only has 51 cards to choose from. Whoa! Guess what she drew? A 5 of clubs. She drew the 1 of clubs. So she had a disadvantage the second time because she only had 51 cards to choose from. Okay, which one was independent and which one was dependent?
Dependent was the second one.
Okay, dependent. Yes, a lot of times the word that you will see with dependent is not replace. And this guy is going to be yes, replace. Does that make sense? You are replacing it. You are putting it back in. That is independent because both of them have an equal chance of getting whatever card you need, right? Versus dependent is not replacing. That's bad. Well, not always bad, but not replacing. Dependent. Okay, so tip 1, identify independent, dependent. Go ahead and read through A, B, C, and put what you think. Independent versus dependent. You can do I and D if you want to. I don't care. I and D. Now, you don't have to actually solve the thing. Just put I or D next to each one. I or D. C is kind of hard, maybe. A says 1 coin lands heads up, and then a second coin lands tails up. What pink? Independent. You're not like shaving a side of the coin off or anything. You have an equal chance of both of those things occurring, and nothing funky is going on. All right. B. 1 student's name is chosen from the jar and not replaced, and then the next student is chosen. That is dependent because if I choose Phoebe as my first name, I no longer have a chance of choosing Phoebe as my second name, right? Because I've taken it out and I've not put it back, right? And then part C, both Wednesday's lottery numbers and Saturday's lottery numbers are 1, 2, 3, 4, 5. Okay, if you know how the lottery works, right? You'll know that like the lottery balls are like put in this big machine and then they pull them out, right? So on Wednesday, do I pull them out and leave them out and not put them back in for Saturday or Sunday or whatever we're doing? Saturday? No, you put them back in. So is that independent versus dependent? Independent, all right? Independent. Now, the chances of them both being 1, 2, 3, 4, 5 is very, very slim to none, right? But it is dependent that there is a chance that that will happen because we put those balls back in. Sorry, I don't know what's going on. It just hates first period. This light bulb hates first period. Sorry. You can't see this on the video, but the board is flickering again. Sorry. All right, example 2. On each turn of a board game, a player rolls a dot cube meaning a dice, or a die if you want the plural of that, a dice, and spins a spinner. Here's what the spinner looks like. On Dion's first turn, he rolls a 3 and then the spinner lands on red. That's this section right here. This is red. Okay? Are these events independent? So what we're doing is we are rolling a dice and then we are spinning a spinner. So dice and then spinner, right? Dice and then spinner. Okay? Now on the dice, let's determine this. Is this dependent or independent? Dice and then spinner. Independent. They both kind of have really nothing to do with each other. So I'm going to put INDEP, or you can just put I don't care, independent. Okay? And then dice and spinner. So I have this guy ready to set up for my proportion, or my fractions. The dice, what am I trying to roll on the dice again? A 3. What are the chances that I'm going to roll that 3? 1 out of 6. There's only one side that has a 3 on it. 1 out of 6, okay? And then spinning the spinner. What are the chances that that spinner is going to land on a red side? 1 out of 3, because that spinner has 1/3. Okay, and then what do I do with those? We went out. Sorry. 1/6 times, and 1/3, what do you do with both of those? You multiply them together. Oh, shoot, I don't know what I'm going to do, because now I have the video. Weird. Okay, 1/6, 1/3, and that, multiply those together, and that makes 1/18. You're going to have to listen. Sorry. My board just turned off. We'll see if we can get it turned back on here in a second. I'm recording, so I can't write up here, otherwise I won't be able to see it, right? Yeah. What a deal. What a deal. Okay, so let's go through. This second one is talking about probability of 2 independent events. You just multiply them together. That's what we just got done doing. Ooh, you can't see what I'm doing. Circle P of A times P of B. P of A times P of B in that little box. You're just multiplying them together. Multiplying P of A times P of B. Okay? Now, example 3. I'm going to talk you through this, and I'll write here, and maybe I'll write up here too. We'll see. Marisol and her friends. So read on your page as I read up here. Marisol and her friends are going to a concert. They put 3 blue off to the side of your paper. List 3B. Like this. 3 blue. Okay? 5 yellow. There are blue and yellow slips of paper. 3 blue, 5 yellow. How many total slips of paper are there? 8. Okay, so I'm going to total them up like this. 8. Off to the side of your paper, put 3 blue, 5 yellow, 8. All right, if a person draws a yellow slip, they will ride in the van. So yellow means van. Okay, van. Are we coming up there? No? Maybe it's van. All right, van. Blue slip, what does a blue slip mean? Car. They're going to ride in the car. So I'm going to put car there and car here. We're back up. Car, van, car. All right. Going back to the board. All right. If a person draws a yellow slip, they ride in the van to the concert. A blue slip means that they ride in the car. All right. Suppose Marisol draws a slip and she doesn't like her outcome. She doesn't like what happens. But she puts the slip back in again. Okay? What is the probability that she draws both of them being blue? What is the probability that on each draw her slip is blue? Okay, is this independent or dependent? Independent. She's putting her slip back again. INDEP. This is independent. She's putting her slip back. So I'm going to do first draw, second draw. Okay, and then I'm going to do my fractions, and we're going to eventually multiply those together. Okay, first draw, second draw. All right, she wants to know her slip being blue both times. Slip being blue both times. What's the chances that the slip is blue the first time? 3 out of 8. 3 out of 8. Now, what is the chances that her slip is blue the second time? What? Did she put the slip back?
Oh, yeah.
Yes, so still 3 out of 8. Yes, 3 out of 8. So, now what you're going to want to do is when you're multiplying these, reduce if you can. So if one of those was 4 eighths, we're going to reduce to 1/2. 3 eighths and 3 eighths won't reduce. So we just have 9 over 64. 9 over 64 is our chances. Somebody have a calculator that you can tell me what percentage that is? What percent chance does she have of drawing the blue twice? What? 37.5% chance. So she has a decent chance that she's going to end up with 2 blue slips, which is what she didn't want, right? Because otherwise she wouldn't have put it back. Does that make sense? So she has a 37% chance.
14%.
What?
14%.
Okay. 14%. Sorry. 40% chance. So, okay, in that case, she's got a pretty low chance of drawing 2 blue slips, right? Which is pretty decent. She doesn't want the blue slip, right? Otherwise, she wouldn't have put it back. So 14% chance is the chances that she's going to get what she doesn't want, okay? That means 86% chance that she's going to get what she wants, right? Okay? All right, now, how would this have changed if we would have said that she's not putting it back? I'm just going to go there, okay? This would be 3 out of 8, and this guy would be 2 out of 7, right? 2 out of 7. Now, we always subtract from the bottom number. 8 becomes 7, right? But why are we subtracting from the top number also? Because they're both blue, right? They're both blue. If this would have said blue and then yellow, we would have 3 out of 8 and then 5 out of 7. Does that make sense? Because we still have all of the yellow. The only reason we subtract from the top number is because we are doing 2 blues in a row and not replacing. That's what he would look like. Does that make sense? Okay, let's go to the back side. Backside, this is what he looks like. Just 14% on that one. Yeah. I was just going through and I'm leading you into this next part where we're talking about dependent, okay? 2 dependent events is the probability of A times the probability of A or B given A, okay? So basically this means subtract out the not replace part, okay? I'm going to put that in here. Subtract out, not replace. So you subtract out the amount that you are not replacing, okay? Example 4, Cynthia randomly draws 3 cards from a standard deck one at a time. We're drawing 3 things. 3 cards, not just 2, 3. So I have 1 fraction times 1 fraction times 1 fraction. I'm gonna go like this. This is my first card. This is my second card. This is my third card, okay? This is how I would set this up every time just so that you don't have to, it just gets your formula ready to go. So all you have to do now is fill numbers in, okay? So I haven't even read the whole problem when I've already got my thing set up. One at a time without replacing them. Underline, circle that word, whatever, without replacing, okay? Find the probability that the cards drawn are in the order of diamond, spade, diamond. Woo. Okay, so how many cards are there in the first draw? Like total? 52, okay? If I'm not replacing, then that means that this guy is 51 and then this guy is 52 again, okay? So I want diamond and then spade and then diamond. How many diamonds are there? 13, okay? So diamond, there are 13, right? Spades, how many are there? 13. And then the last one is a diamond. How many are there? Oh, why did 52? I don't know because I'm not awake yet this morning. Sorry, 52, 51, 50. That's what I meant to say. Yes. Well, I think that's what I said, but maybe it didn't come out my fingers that way. I don't know, whatever. Anyway, so India said diamond again is 12. Why is it 12 now? Because this guy was a diamond, and we are assuming that we did in fact pull a diamond out. So there are only 12 of those left, okay? So diamond the first time is 13. Spade the first time is 13, but then we're drawing a second diamond, which means there's only 12 left. So we're going to do that, but let's reduce to start with. What is 13 out of 52 reduced to? 1/4, right? That makes it really nice. 1 over 4, okay. 13 out of 51 I don't think reduces, but just 12 out of 50. I know we can at least divide by 2, right? So this is 6 out of 25. Maybe? 13 is a prime number, so that won't reduce with anything else, but then 6 and 4 can reduce. Can we do that? You can reduce top and bottom. You can reduce anything that's like diagonally as well. So 6 and 4, can we reduce those? Yeah. Does that make sense? Okay. So this 6 is going to reduce with this 4 because one's on the top and one's on the bottom. So this guy becomes 3 and this guy becomes 2. So on the top, I have 1 times 13 times 3. Do you see those numbers? 1, 13, 3, that's 39 all over. 2 times 1 times 25. Okay, blah, blah. 2 times, I'm just trying to confuse you this morning. 2 times 51 times 25. Woo! 2,500 and what? 50? 25, 50? And there we go. What is that as a percentage?
1.5%.
1.5%. So if I were to bet money on this, would you bet all the money that you have that you're going to draw a diamond, a spade, and then a diamond? No, because it's only like less than 2% chance that that's even going to happen, right? All right, so example 5, last one. In a carnival game, 3 cards are marked with stars. I'm going to put that off to the side over here. 3 stars. 3 cards are marked with circles. All 6 cards are placed face down, and the player turns over 2 cards, one at a time. Blah, blah, blah. This is getting kind of confusing, okay? Turns over 2 cards. So I'm going to do this times this. 2 cards. This is going to be my first card, and this is going to be my second card, okay? If the first card is a star and the second card is a circle, the player wins, okay? So before I even read this bottom part, let's find the chances of that happening. The first card being a star and the second card being a circle, okay? Now, if we are flipping them over, are we replacing or are we not replacing? It doesn't say. Are we replacing or not replacing? We're flipping one over and then we're flipping another over. So this one doesn't go back in, right? So we are not replacing. I'm going to put that up in here. Not replace. So we had 6 cards to start with, and then if we are not replacing, then we have 5 cards left. Okay? We want what first? We want a star first. How many stars are there? 3. And then we want a circle after that?
3.
And there are 3. Okay? So 3 out of 6, I can reduce that. That's 1/2, right? Anything else I can reduce? Even like diagonally or anything like that? Nope. 1 times 3 is 3. 2 times 5 is 10. What percent chance is that of happening? 30% chance that that's going to happen, right? 30% chance that that exact scenario that I'm going to win, right? So Alex decides, I'm reading this paragraph down here. Alex decides to play the game only if he has at least 25% chance of winning. Should he play the game? Yes. Yes. He has more than 25% chance of winning. Make sense? This is not too bad, right? Multiplying? Yeah. I don't know why they don't teach this lesson first before you get to permutations and that other junk. Yeah, those are kind of nasty. Now, they will probably try to trick you with some homework problems. Guarantee you they'll do some hard stuff. But think about what it means. Like this last problem, they didn't tell me that I wasn't replacing. So you got to think about, if you're doing that, are you replacing or not? Okay, so be careful. That is the video that I have for you, yearbook girls. There you go. I'll post the homework assignment on Classroom as well. Okay?
Bye.
Goodbye. Everybody say bye.
Bye.